You think going to Mars is the hard part. The rockets, the distance, the radiation, the months of isolation in deep space, every documentary, every space agency animation, every ambitious headline frames Mars as a destination problem. How do we get there? How do we land? How do we survive? But the most dangerous assumption hides inside a quieter question. How do we come back on Earth? Return feels automatic. You board a plane, you land somewhere else, and eventually you fly home. Even missions to the moon created a psychological template. Land, explore, launch, return. It feels like a symmetrical act, departure and return as mirror images. But Mars is not the moon, and symmetry is an illusion. You think space travel is about distance, but in reality, it is about energy. To leave Earth, you must escape its gravity. Well, that requires enormous velocity, roughly 11 kilometers per second, just to break free. Rockets burn vast amounts of fuel to achieve this, shedding mass in stages, because carrying fuel to carry fuel becomes impossible beyond a point. That's the first gravity well. Mars has one too. If humans land on Mars, they will descend into another gravitational trap, weaker than Earth's, yes, but still real. To leave Mars, you must again accelerate to escape velocity. You must launch from a planet with limited infrastructure, limited fuel production, limited margin for error. And here is where the illusion collapses. On Earth, launch failures are tragic, but recoverable in the sense that the planet itself supports rescue, redesign, and repetition. Mars offers no such redundancy, no emergency runway, no nearby station, no supply chain. You think a Mars mission is a one-way challenge of reaching a distant world. But it is actually a two-stage problem. Escape Earth, survive Mars, and then escape Mars with whatever you manage to bring or manufacture there. The energy requirements stack. Every kilogram you land must either be brought back or left behind. Every kilogram of fuel needed to return must either be transported across millions of kilometers or produced on site using technologies that must function flawlessly in an alien environment. And all of this must be calculated years in advance, because Mars and Earth do not simply sit still in space waiting for each other. They orbit the Sunday at different speeds. The window for an efficient return trajectory opens only at specific alignments, roughly every 26 months. Miss that window, and you wait. You think return is just the reverse of departure. But orbital mechanics does not work that way. A return from Mars is not simply pointing a rocket at Earth and firing engines. It requires precise timing, precise energy budgets, and an intricate dance with gravity itself. The deeper truth is unsettling. Going to Mars is a test of engineering. Coming back is a test of physics. And physics is not negotiable. To understand why returning from Mars is so unforgiving, you have to confront a formula that quietly governs every launch ever attempted. It is called the rocket equation. You might imagine that a rocket works like a powerful car engine. Add more fuel, burn longer, go farther. It feels linear, intuitive. More fuel equals more distance. But the rocket equation destroys that simplicity. In spaceflight, fuel itself has mass, and that mass must be accelerated along with everything else. The more fuel you carry, the heavier you become. The heavier you become, the more fuel you need to accelerate that mass, which makes you heavier still. You think adding fuel solves the problem, but in rocketry, fuel is both solution and burden. This exponential trap is why rockets launch in stages. They discard empty tanks to shed mass as they climb out of gravity wells. Without staging, escape becomes nearly impossible. Now imagine standing on Mars. You are on a planet with about 1/3 of Earth's gravity. That sounds forgiving. But to leave Mars, you still need to reach roughly 5 kilometers per second. Not trivial, not optional. And here is the uncomfortable part. If you want to return to Earth, you must have the fuel ready before you ever leave Earth. You think the mission ends when astronauts land. In reality, the return journey must already exist in potential energy. locked inside fuel tanks or in the capability to manufacture that fuel on Mars. But carrying return fuel from Earth multiplies mass dramatically. Every kilogram you bring to Mars must be launched from Earth first. And launching from Earth is the most expensive energetic step of all. So mission designers propose producing fuel on Mars itself, using carbon dioxide from the Martian atmosphere and hydrogen brought from Earth. They can create methane and oxygen. In theory, but theory is not redundancy. You think machines fail occasionally. On Earth they do. On Mars, failure is terminal. The fuel production system must survive landing. It must operate in extreme cold. It must handle dust storms that can last for months. It must function without immediate human repair support. And it must produce enough propellant to lift a crew vehicle off the Martian surface. If it underperforms, there is no backup station over the horizon. Now consider orbital mechanics. Leaving Mars is only the first step. Once in orbit, the spacecraft must execute a precisely timed burn to intersect Earth's future position. Earth will not be where it was when the astronauts departed. Both planets are moving around the sun. Miss the window, and the energy cost rises sharply. You think you can just burn longer to compensate. But fuel margins are finite. Every correction requires propellant. Every miscalculation compounds. And then there is re-entry. Arriving at Earth from interplanetary space means entering the atmosphere at tremendous speed. Heat shields must perform flawlessly. Trajectories must be exact, too shallow. And you skip off the atmosphere back into space, too steep, and you burn. The return is not a mirror image of departure. It is a cascade of constraints: energy, mass, timing, reliability. The rocket equation does not care about ambition. It does not negotiate with optimism. It simply tallies mass and velocity. And when you run the numbers honestly, you begin to see why returning from Mars is not merely difficult. It is unforgiving. The deeper difficulty of returning from Mars does not lie in rockets alone. It lies in geometry. You think space is empty and straightforward. Point in the right direction, accelerate, and you arrive. But interplanetary travel is not navigation across a blank map. It is movement within a gravitational system where everything is already in motion. Mars does not wait for you. Earth does not wait for you. Both planets orbit the Sunday at different distances and different speeds. Earth completes one orbit in about 365 days. Mars takes roughly 687. By the time astronauts land on Mars, Earth has moved far along its own path. Returning requires intercepting a moving target across millions of kilometers. This is why missions rely on what is called a transfer orbit. Instead of flying directly toward where Earth appears to be, a spacecraft must launch into an elliptical trajectory that intersects Earth's orbit at the precise time Earth arrives there. It is less like throwing a dart and more like predicting the future position of a drifting platform. You think travel is about distance. In reality, it is about timing. If the return launch from Mars is even slightly mistimed, the spacecraft may miss Earth's orbital position by millions of kilometers. Correcting that error mid-flight demands additional propellant, which may not exist. And timing is not flexible. Launch windows between Earth and Mars open only when the planets align favorably. This occurs roughly every 26 months. If a mission lands on Mars shortly after such a window closes, the crew must wait for the next alignment before attempting return. That waiting period can last over a year. During that time, systems must remain functional. Life support must endure. Psychological strain must remain manageable. You think the danger lies in the dramatic moment of launch, but much of the risk hides in prolonged exposure to isolation and radiation. Deep space is not empty in the sense of harmlessness. It is filled with high-energy particles from the Sunday and beyond the solar system. Earth's magnetic field shields us from much of this radiation. Mars offers minimal protection. A crew waiting for the correct return window accumulates exposure that cannot simply be undone. Even if everything works perfectly, Orbital insertion upon arrival at Earth is not trivial. A spacecraft returning from Mars approaches Earth at velocities far higher than those of a vehicle descending from low Earth orbit. The energy difference is immense. Managing that energy safely requires precise trajectory design and robust thermal protection systems. But the real conceptual challenge lies deeper. Returning from Mars is not just escaping one planet and arriving at another. It is transferring between gravitational wells, embedded in the Sunday's larger gravitational influence. The spacecraft must carefully adjust its velocity relative to the Sunday, not merely relative to Mars. You think gravity acts like a simple pull downward, but in interplanetary travel, gravity shapes curved paths through space-time. A spacecraft coasts along these curves, occasionally firing engines to reshape its trajectory. Those engine burns must be calculated years in advance, simulated repeatedly, and executed within narrow tolerances. There is no roadside assistance in heliocentric orbit, and there is another layer of fragility. Every system aboard the return vehicle navigation, propulsion, structural integrity, guidance must survive months on the Martian surface before being asked to perform flawlessly. Dust infiltration, thermal cycling, material fatigue all accumulate quietly. On Earth, hardware can be inspected in controlled facilities. On Mars, maintenance occurs in a hostile environment with limited tools and limited spare parts. You think of return as a heroic final act, but it is really the culmination of thousands of prior decisions, each one narrowing the margin for error. Orbital mechanics is not forgiving because it is not negotiable. It is governed by conservation laws, energy, momentum, angular momentum, that do not bend to human urgency. If the trajectory is wrong, it remains wrong. If the fuel is insufficient, there is no workaround. Returning from Mars requires aligning mass, velocity, planetary motion, radiation exposure, life support durability, and human resilience within strict physical limits. And those limits are set not by engineering optimism, but by celestial mechanics, which leads to a sobering realization. The challenge is not simply that Mars is far away. The challenge is that space itself demands precision that leaves almost no room for second chances. By now, the difficulty of returning from Mars seems mathematical. Fuel ratios, orbital windows, escape velocities. But behind every equation stands a human body. And human bodies are not equations. You think the problem is propulsion. In truth, propulsion is only one constraint layered onto biology. A crew traveling to Mars will spend months in microgravity. In that environment, bones lose density, muscles atrophy. The cardiovascular system adapts to weightlessness. Astronauts aboard the International Space Station exercise for hours each day to counteract these effects, yet measurable decline still occurs. On Mars, gravity exists, but it is only about 38% of Earth's. That partial gravity may not be enough to prevent further physiological change. No human has lived for years in such conditions. We do not know precisely how the body will respond over long durations. Now imagine that same crew preparing for launch from Mars. Launching from a planetary surface imposes intense forces. Acceleration presses bodies into seats. Blood shifts. The vestibular system strains. A crew weakened by prolonged exposure to radiation, isolation, and altered gravity must endure that stress without failure. You think machines are the fragile component, but biology carries its own limits. Then there is psychology. A Mars mission is not a brief expedition. It is a commitment spanning years. Communication delays between Earth and Mars can stretch to over 20 minutes each way. Real-time guidance disappears. Conversations fragment. Support becomes asynchronous. If something critical fails during return preparation, Earth cannot intervene immediately. The crew must diagnose, repair, and decide under pressure, knowing that mistakes cannot be undone. Isolation compounds risks. You think training can eliminate uncertainty, but no training environment replicates the knowledge that rescue is impossible. On Earth, even remote research stations retain some connection to civilization. On Mars, a crew becomes a self-contained ecosystem, entirely dependent on closed-loop life support systems, oxygen recycling, water reclamation, food management. Each subsystem must remain operational not only for survival on Mars, but for the return journey itself. And redundancy is expensive. Every backup system increases mass. Every kilogram adds fuel demands. Engineers must balance safety against feasibility. Perfect redundancy is impossible, so trade-offs are made. The return vehicle may sit on the Martian surface for months or years before launch. During that time, it must endure temperature swings that range from extreme cold to relative warmth. Dust storms can envelop the planet, coating surfaces in fine particles that infiltrate seals and mechanisms. Components age. You think time is neutral. In space exploration, time erodes margins. Radiation exposure adds another invisible constraint. Galactic cosmic rays and solar particle events damage cells and increase long-term health risks. Shielding adds weight. Less shielding reduces safety. There is no perfect solution. By the time a crew initiates return, they are not the same as when they departed Earth. Their bodies, equipment, and environment have all changed. And still, the rocket equation remains waiting. All the precision of orbital mechanics, all the unforgiving mathematics of fuel mass and velocity, now intersect with the unpredictability of human endurance. Returning from Mars is not just about escaping gravity wells. It is about carrying fragile biology through a system optimized for celestial objects, not living organisms. Physics sets the stage. Biology performs upon it. And the margin between success and catastrophe is thinner than most people imagine, because once the engines ignite on Mars, there is no pause button. There is only commitment to the trajectory. When people imagine a mission to Mars, they picture the landing, the red horizon, the first footprint, the symbolic triumph of becoming a multiplanetary species. But the real warning is quieter. It is not that Mars is unreachable. It is that Mars does not forgive. Physics does not celebrate ambition. It does not reward courage. It simply enforces conservation laws without exception. Every kilogram must be lifted. Every meter per s-econ must be earned. Every trajectory must obey gravity's geometry. You think exploration is about bravery in spaceflight. It is about margins. Returning from Mars forces humanity to confront a hard truth. We evolved in a gravitational cradle with abundant atmosphere, magnetic shielding, and immediate redundancy. Earth is not just our home. It is an extraordinarily forgiving environment. Mars is not. The energy required to escape Earth is immense. The energy required to escape Mars is smaller, but it compounds with interplanetary transfer demands. The rocket equation amplifies small miscalculations into exponential consequences. Orbital mechanics restricts freedom into narrow windows. Human physiology introduces variables that cannot be reduced to clean equations. None of these constraints are dramatic in isolation. Together, they form a lattice of fragility. You think the danger lies in distance, but distance is merely a symptom. The deeper issue is that space travel operates in a regime where error tolerance approaches zero on Earth. Failure is often survivable. On Mars, failure accumulates until it becomes irreversible. This is the real warning embedded in the physics. Not that return is impossible in principle, but that it is unforgiving in practice. Every system must function across years. Every assumption must hold under stress. Every calculation must align with celestial motion that does not pause for correction. The more honestly you examine the numbers, the more you recognize that a Mars return mission is less like a round trip and more like threading a needle across millions of kilometers with gravity tugging at every stage. It can be done. But it cannot be done casually. And perhaps that is the deeper lesson. Human ambition expands naturally. We look outward and assume that if we can reach something, we can return from it. But physics reminds us that expansion carries cost. That movement through space demands energy in quantities that reshape engineering, biology, and risk itself. Mars does not forbid return. It simply demands that we respect the architecture of the universe. And in that demand lies both the challenge and the warning.